Now, I often come down a little bit hard on the textbook as not being necessarily very well oriented around teaching students. But I think in this case, they do actually a fairly good job illustrating what this wind shear looks like when we're talking about just a change in the wind speed. This is an actual figure from your textbook. I scanned it. It's page 81. And as long as you have a little explanation as to what this figure is doing, it's actually not terrible. Uh, if we just pick one isobaric surface, okay, so see how we got a coordinate system here. We got X, we got Y, we got Z. And we are looking at an isobaric surface there that I've highlighted in red, where we're at that pressure P naught plus delta P. I didn't use the very bottom one, I just worked on the middle one. And so we're trying to look at this with a perspective here. The part that's darker red is closer to us, and the part that fades to pink and white is farther away from us. And we're just trying to look at this at a perspective. Now, this diagram shows it as if that's the x-axis moving off to the right, and that is a fairly standard way of looking at such things. On the other hand, it doesn't make a huge amount of sense in terms of the meteorology of this. If you're already thinking, why would the height surfaces be closer to the ground? Why would an isobaric surface be closer to the ground in the west and farther from the ground in the east? Wouldn't it have been better if, like, they had drawn the perspective differently so that the height surface was closer to the isobaric surface was closer to the ground in the north and farther from the ground in the south? Yes, I wholeheartedly agree. Again, a good example of this not being necessarily a book very well oriented at all around teaching dynamic meteorology, but that's neither here nor there. All right, we have a given little isobaric surface there, and what the book is trying to help us see is this geostrophic wind vector. Now, I highlighted it in red on our red surface there. So we have a geostrophic wind vector right now that is in that direction. It's headed off like parallel to the y-axis in this case. Okay, I could picture we might have a geostrophic wind at some, maybe this is the, let's say this is the 850 millibar surface that we're looking at right now here in red. I could picture that being the a 850 millibar geostrophic wind heading straight to the north or something like that. Okay, I could see that. And how we would come up with that direction for the geostrophic wind would have to do with the orientation of the height contours, which I have drawn in there as those red lines. The geostrophic wind will be parallel to them, and the magnitude of the geostrophic wind will have to do with how far apart those height contours are. Notice that those height contours there are nice little examples of level curves. That's just borrowing a term from calculus or whatever. I'm just trying to show you here that, each of those those red lines I drew on there is like where a particular height above the ground on the z-axis slices through our isobaric surface there. Anyway, so we have some height contours on this map on the red level there. Again, let's call that maybe 850 millibars. Now we could pick another isobaric level, and I'll color it here blue. Maybe that blue one is 500 millibars. It's someplace higher above the ground anyway than that red level was. Your book shows it as being P naught plus 2 delta P, where delta P is apparently a negative number, but whatever. They never return to that notation in this book, so it doesn't really matter. Anyway, so here's a new surface that I've got up there in blue. Again, it's kind of hard to see because the perspective is a little bit artificial. It's vanishing off into the distance, though. The parts that are darker blue are closer to us, and the parts that get lighter blue and then fade off into white are farther away from us on that surface. And if that geostrophic wind vector that I have on there, which I highlighted in blue, is going to be stronger than the one that was at a lower level, which, again, they just illustrated with a smaller, shorter vector. Okay, I can picture this here. Again, let's think that is like maybe a 500 millibar surface that I have there in blue, and then in that case, the 500 millibar geostrophic wind at that location is still straight, out of the south and heading towards the north. It's just going to be a stronger wind. Okay, I can see that. I can wonder how we're going to get that. Well, the direction, of course, is going to have to do with the orientation of the height contours on that 500 millibar surface, which I've drawn some of them there as those solid blue lines. But in order to make the wind speed stronger, the only thing that determined the speed of the geostrophic wind was the spacing of the height contours themselves. So if the wind at 500 millibars, if the geostrophic wind, that is, at 500 millibars is going to be stronger, we're going to have those height contours closer together than they were at the red level. So see how at the red level, those contours were fairly far apart, and then on the blue level, rather, they're fairly close together. In order to get that stronger wind speed for the geostrophic wind at the blue level, we're going to have the height contours closer together. We're going to have more of a slope to our isobaric surface. Now, this is where the book starts making some of the notation a little bit more clear. See how there is a distance between each of these two surfaces, the red one and the blue one. Maybe that's 850 and 500 millibars or something like that. And the distance between those surfaces, the book is using this notation delta Z, where that little delta Z is just going to be a measure of literally how many meters it is between those two isobaric surfaces. Now, if that delta Z were a constant, then the spacing between that red and that blue isobaric surface really wouldn't be changing. It would not changing with respect to time, but changing from location to location. The two surfaces would basically be parallel to each other. That would mean that the height gradient would be exactly the same on the two surfaces, because if whatever it was doing on one surface, the other surface is parallel to it, it's going to have the same slope as the first surface did. And, well, if the slope of that isobaric surface is what determines the speed of the geostrophic wind would be the same on both of those two surfaces too, if they were evenly spaced, if that delta Z was a constant. But delta Z is clearly not a constant here. It clearly, in this case, is varying with respect to x. And again, just to make that a little bit more clear, this is the x-axis here along this way. And so at two different locations along the x-axis, like in this case, this x1, we have one value of delta z1, whereas at a different location along the x-axis, x2, we have a different value, delta z2. That is, so the distance between the red isobaric surface and the blue isobaric surface is changing as a function of x. Okay. Hold on here.